Okay, so chemistry. The basic unit of all chemistry is the atom. You're welcome, chemistry, said physics. Okay, all right. So the atom is the basic unit of all matter. Okay, it is the smallest piece of matter that retains the properties of the elements. Okay, are there things smaller than the atom? Obviously. Okay, but the atom is the smallest unit of something that retains all the properties of that material. So we call it the smallest unit of matter. Okay, so we're going to look today at the theories of the structure of the atom. Kind of a progressed through history. It looked, initially people thought it looked like this, and then they thought it looked like this, and why? Okay, and then we're also going to look at that in the context of why did what we think the atom looked like change? Why does it still sometimes change? Okay, as a examination of the scientific process. Okay, we have this idea, but we discover something, and this thing we discover no longer fits with the idea. So we have to change the idea. We can't change the results of an experiment. The experiment says this. Then we have to change our ideas. That's how science works. Okay, experiments lead to new discoveries, which change the way we think about things. Okay, and science is a good example of that. Science also has bad examples of that. Okay, for the longest time, science tried to group all life into two kingdoms. You were either a plant or an animal. Okay, and that thought process persisted for a very long time, even though we knew lots of things didn't fit into those two categories. We just forced them in there because it was easier than changing our thinking. Okay, that's not good science. Okay, we don't do that anymore. Okay, now there's five kingdoms. Okay, and that makes way more sense. So, because obviously, like a mushroom would have been in the plant kingdom. Is a mushroom a plant? No, it doesn't carry out photosynthesis. Okay, its cells look way different than most plant cells. It's not a plant. Okay, but it grew out of the ground, so we put it there. Okay, and so yeah, just things like that didn't make sense. Like all bacteria were also put in kingdom Plantae because they had cell walls. They're not plants, so it just didn't fit. So we revise our thinking as we discover new things. All right, we'll also review the parts of the atom and their characteristics. Okay, so that's what we'll be looking at today. Okay, so the earliest work done in chemistry, okay, on purpose, would have been the alchemists. Okay, the alchemists were a group of people, kind of, in the Dark Ages, really. Okay, they would have been your very stereotypical scientist who lives in this dark room and's got all these boiling potions and things like that. Okay, those were alchemists. Okay, it wasn't a true science because a true science involves using the scientific method, which wasn't developed yet. Okay, alchemists basically just mixed stuff together and saw what happened. Okay, so I'm sure gunpowder was invented several times, but they didn't live to tell anyone about it. Okay, things like that. What were they trying to do? Well, they weren't trying to progress science. They were trying to get rich. They wanted to develop things that we now know are basically impossible. Okay, they wanted to develop the elixir of eternal life, and they wanted to be able to transmute cheap metals into valuable metals, like lead into gold. Okay, and things like that. Things that we know now are not possible. Okay, problem was that some people believed what they did was possible, and they were drinking mercury and stuff like that. Oh yeah, drink this stuff; it'll make you live forever, and you die 2 days later. Okay. So yeah, that's kind of what the alchemists did. It was very much a trial and error type of thing. And of course, because they were trying to get rich, they weren't sharing their experimental data with each other, right? Which doesn't help a science to progress, which is why alchemy was not a science. Okay, it was people trying things. Okay, in the process of alchemy, people did learn a lot about the behavior of matter. So it wasn't a total loss. We did learn a lot of things about how matter behaves, and that allowed us to move that kind of stuff into a true science of chemistry later. Okay. Obviously, we also knew that chemical reactions could be used to do useful things like dye cloth, tan leather, prepare or preserve foods. Okay, people knew that matter had certain properties and could be used to do things, and that was, again, not chemistry, it's more technology. Okay, the idea of the atom, believe it or not, has been around for thousands of years. It just wasn't widely accepted. Okay, the first person to come up with this idea was a Greek thinker named Democritus. Okay? And Democritus, by the way, being a Greek thinker was like the sweetest job you could have in ancient Greece. Okay, you sat in the Parthenon and people waved palm fronds and gave you grapes, and you sat there and thought up stuff. Okay, some of it good, some of it not so good. All right, so Democritus had this idea that all matter was made of these tiny, indivisible particles called atoms, not invisible, indivisible. Okay, which meant you couldn't split them. Right. So the day he thought that idea up was not a good day for him, because people went, he's been in the sun too long. He's talking about tiny invisible things that we can't see that make up everything. Why can't he just say everything's made of the four elements like Plato does? Okay, and so it wasn't widely accepted. It didn't catch on. Democritus thought about it a lot. He wrote down a lot of why he thought this idea worked, but it didn't make sense to the general populace, so it wasn't accepted. Okay? What was more acceptable was what made sense. Okay, I mean, the Greeks had kind of a rudimentary periodic table. Okay, they knew everything was made of the four elements. Okay, the four elements were earth, water, air, and fire. Right. Okay, and they knew that everything was a mixture of those four elements. Okay, lava was some parts earth, some parts fire, and some parts water. Okay, made sense because it flowed like water. It came out of the earth and it was hot. Okay, so it made sense that it was some parts of those three elements. Okay, steam was some parts fire, some parts water, and some parts air. It made sense. You mix those three things to get it, fire and water, and you get steam. Okay, so it made sense to them. And so why would they say, oh yeah, let's go with this idea of these invisible particles that don't make any sense? All right, so it wasn't widely accepted, it didn't catch on, and it was forgotten about for thousands of years, even though he ended up being right. Okay, we now know that yes, matter is composed of these tiny indivisible particles. Okay, all right. Wasn't all bad for Democritus. He did come up with something good. Kind of sounds like his name. Democracy. Yeah, so it wasn't all bad for him. He just went into politics. So. Okay, during the Middle Ages, so we talked about the alchemists here. Their goal was to change common substances into gold. They weren't ever successful because you can't do that. Okay, gold is an element. I can't change the atoms of lead into atoms of gold. That just doesn't happen. The atoms are different. They have different numbers of protons and neutrons and electrons. I can't transmute something into something else. Okay, was it logical though for them to think they could? Yes, because lots of times when they mixed things together in a chemical reaction, what they got at the end, the products, were very different than the starting materials were. Okay, I mean, you think about it, if you mix vinegar and baking soda, it's a very simple, basic reaction, right? You start out with a powder and a liquid, and you get a gas out of that, right? You get a gas in this solution afterwards. They saw evidence that if I take this metal and I put it in here, it dissolves or it changes color, or whatever. It made them think, yeah, there's got to be a way to turn this material into this material, and once I figure it out, I'll be rich. Okay, it made sense for them to think that because they didn't know about the atom. They didn't know about you not being able to change one atom of something into something else. Okay, so they worked on it hard for years and years and failed. Okay, all right. After the Alchemists, a couple hundred years after the Alchemists, okay, Roger Bacon and Antoine Lavoisier came along, and they were looking at kind of what was going on in alchemy and a few other things. And they said, this could be a lot better if everybody went about experimenting in the same way. So they developed what we now know as the scientific method. Okay? That's what turned alchemy into chemistry, okay? And into a valuable science that contributed a lot of knowledge and technology to the world. Okay? So to turn alchemy into chemistry, okay, and into a true science, we had to go from trial and error, random things, to a very methodical approach. Okay? In the scientific method, what do you start with? Even before that, what are you going to investigate with a science? Starts with P. All labs start with this. A question or a problem. Yeah, okay? We start out with a problem, okay? So you start out with a problem, and then you come up with a hypothesis, okay? Your hypothesis is a tentative answer to the problem. It's a really layman's way of saying it. A hypothesis is really an if and then statement that says, if this is true and an experiment like this is run, then the results will be this. Okay, it's a predictive statement that deals with the problem. Okay? From there, you come up with your variables. Essentially, you design your experiment. You say, okay, in order to test my hypothesis against this problem, I'm going to run an experiment where I change this, I measure and record this, and I control everything else. I keep everything else the same. Okay, that's part of the scientific method as well. So you're manipulated, responding, and controlled variables. That's all part of the scientific method as well. Okay, once you have your observations, you've run your experiment, then you analyze them. So you have your analysis, then you have your conclusion, okay, where you say my hypothesis is acceptable or not acceptable because the data says this, and then you are done. Okay, that's the scientific method. That sort of makes sense? Okay, that was Roger Bacon and Antoine Lavoisier. That was their big contribution, and all science now uses that. All right, so now on to the atom. So now we have chemistry. Now we'll talk about, okay, the history of the atom. So if I take a chunk of something, let's say lead, okay, and I start cutting it into smaller and smaller pieces, are all the pieces still lead? Yeah, okay. I can keep cutting it. Well, I wouldn't have a knife this small, but let's say I could keep cutting it down until I had just single atoms of lead. Are they all still lead? They also have the same melting point, boiling point, density, all of that. They all retain the same physical properties. Okay. Now, originally, that's where we thought it stopped. Nothing could get smaller than the atom. Okay. We now know, of course, that's not true. There are smaller things in an atom. And we also know that an atom is divisible. Okay? We've done it. We've split the atom. Okay? It's not easy, and you can't split all atoms. Okay? But we know that atoms can be split. But if we do that, are they still the same atom as before? Okay. In a nuclear reactor, in a nuclear fission reactor, you split atoms of uranium. When you're done, are they the same? No. Okay? They change into other things. Okay? They change into what we call isotopes. Okay? That is atoms that have different numbers of neutrons than they're supposed to have. Okay? And there's all kinds of different radioactive products that come from that reaction. So we do know that we can actually split an atom, and that will change it. It will change its physical properties, its chemical properties, and all of that stuff. Right? But it doesn't happen so much in nature. Okay? It's kind of an artificial process. Okay? Some things are radioactive and decay, and that is a natural process. But what we do in a nuclear reactor is that process accelerated, okay? Massively accelerated. All right, we'll talk about that in a little bit. Okay, so if I keep cutting it down, eventually I'll get to the point where I can't cut it any further and still retain the properties of, in this case, lead. Okay, that particle or that chunk of the material would be an atom. Okay, the smallest part of an element that retains the properties of that element. So that's kind of the definition of the atom. Okay. Now, that's great. It's a great idea. But when this idea was first proposed by Democritus, it didn't go over well. Okay. And when it was proposed again later by John Dalton, the first question from everybody was, what does it look like? Because we're naturally, visual creatures. What does an atom look like? I don't know. It's tiny. Like I just finished telling you how much I'd have to cut this chunk of lead to get one. Okay, I have no idea what it'll look like. So he kind of just went with a sphere. Made sense, when we looked at natural occurring objects, stars and planets and moons, and they were all spheres. So all right, it's a sphere. Okay, no one was going to be able to prove otherwise, not for a couple of 100 years. So okay, let's go with that. It's a sphere. Okay, and people are like, okay. Okay, we didn't know about protons, neutrons, electrons, or anything like that yet. So okay, that makes sense. It's a sphere. All right, and so that was Dalton's initial proposal. Okay, Dalton came up with the initial atomic or the original atomic theory. Okay, or particle theory. Okay, these 4 points are definitely something you're going to want to know. All right, so if you have the notes package, you want them highlighted, circled, okay? These 4 points form the basis for our understanding of the behavior of matter. Okay, first and most important point, stolen from Democritus. Okay, all elements are composed of tiny, indivisible, not invisible, indivisible particles called atoms. Okay, atoms comes from the Greek word atomos, which means uncuttable. Okay, so like I said, these 4 points are Dalton's atomic theory. Okay, the second point of the atomic theory talks about the nature of atoms of the same element. So atoms of the same element are identical. We know that's, for all intents and purposes, true. There are some called isotopes that are slightly different. We'll talk about that later. Okay, so atoms of the same element are identical. Atoms of any one element are different from those of any other. Okay, so if I have a tank full of oxygen, every atom in that tank is identical. Okay, every single one of those atoms will have 8 protons, 8 neutrons, and 8 electrons. That's just the way it'll be. They'll all have that. Okay, the same is true for any other element. Okay, in fact, the properties of an element are based on how many protons there are in the nucleus. Okay, that's what makes all the elements on the periodic table different. Every element has a different number of protons in the nucleus. Okay, points 3 and 4 deal with the behavior of matter when it's changing. Okay, so for point number 3, it says atoms of different elements can combine with one another in simple whole number ratios. That's important. Whole number ratios. You'll never have a compound that has half an atom in it. Okay, because we just said atoms are indivisible. Okay, yeah, we can split them, but that's not a chemical process. That's a physical process. Okay, so atoms can combine, and when they do, they'll form molecules and compounds. Okay, but they do so in whole number ratios. Okay, examples could be sodium chloride, okay, table salt, okay, or water. Okay, whole number ratios. In sodium chloride, the ratio is 1 to 1. Right? There's 1 sodium for every chlorine. In water, the ratio is 2 to 1. There's 2 atoms of hydrogen and 1 atom of oxygen. Okay, but I have to write it like this: 2 and 1. We don't write the ones, but there's 1 here. Okay, I would never write it like this. That's still a 2 to 1 ratio, but it's not a whole number ratio anymore. It's 1 to 1/2. And I can't have half an oxygen atom. Half an oxygen atom is beryllium. Okay, not the same thing. Okay. Okay, so point number 3 just talks about how compounds and molecules form and what atoms do when that happens. Point number 4 was the final nail in alchemy's coffin. Okay, because remember, alchemy was trying to change one thing into another, transmute lead into gold, turn one element into another element. That can't be done because in a chemical reaction, in chemical reactions, okay, atoms can be separated. So I could like separate sodium from chlorine. I can't pull sodium apart, but I can pull sodium and chlorine apart in a chemical reaction. Okay, they can be joined. I can put 2 things together. Put hydrogen and oxygen together, I get water. Okay, or they can be rearranged. Okay, an example could be something like this reaction here. I could have potassium iodide reacting with lead nitrate. Okay, in this reaction, my products would look like this. Okay, so I know we're not there yet. We're not into writing chemical reactions, but all I want to illustrate here is, did I make anything new? Right, I rearranged them, right? I still, on this side here, I had potassium and iodine and lead and nitrogen and oxygen. And I have all the same things over here, okay? I didn't get any new elements from this chemical reaction. Atoms can be separated, they can be joined, they can be rearranged, but I can't turn one into something else. Okay, so in a chemical reaction, I'm never going to have a chemical reaction where suddenly an element appears on one side that wasn't there before. Okay, I can't do that. In a physical nuclear reaction, I could. Okay, that can happen. In a nuclear reaction, I can get atoms that are changed, okay, but not in a chemical reaction. In a chemical reaction, they can be separated, joined, or rearranged. So all the stuff the alchemists were trying to do, okay, was this. That's what they were doing. Okay, they can't just go like this, plus whatever. Okay, you can't just make lead turn into gold and something else. Okay, that's not possible. All right, everybody okay with that? Okay, so this whole thing about like changing the atom, okay? So I'm gonna tell you how you make a nuclear bomb. I can do that because you can't get your hands on the materials. It's way harder than I'm gonna illustrate it to be, okay? But for all intents and purposes, okay? A nuclear bomb contains a shaped charge, so explosives, okay? So this whole octagon would be made of like C4, okay, plastic explosive. Okay. And in the middle would be a big chunk of your fissionable material, uranium, plutonium, okay, something like that. So in a nuclear bomb, there's actually two explosions. There's the detonation of the explosive, and then there's the nuclear reaction. That's the mushroom cloud and all the bad stuff, okay? So what happens is when we detonate this charge, particles are shot inward because it's shaped to kind of focus the energy onto the chunk of fissionable material. Okay, so this stuff here, the fissionable material, are made of really big, unstable atoms. Okay, they're already radioactive. If they're radioactive, it means that they're already kind of on their own, breaking down into other things. Okay, so what we do is accelerate the process by setting off an explosion that shoots small particles at high speed towards this chunk of stuff that just wants to split. Okay, so when they collide with it, it starts a chain reaction of atoms hitting each other, pieces of atoms hitting other atoms, and they all split. Okay, when they split, they release huge amounts of energy. Okay, and afterwards, we have different atoms. Okay, we might go from like uranium 238, okay, would be the initial like fissionable material inside, and we might end up with plutonium, or we might end up with lead 238, or like other things like that. Okay, different materials, okay, different atoms, because the numbers of neutrons and protons have changed, because when the atom got hit, some of the neutrons and protons came off. Okay, and when they came off, that's what released all the energy. Okay, that sort of makes sense? So in a nuclear bomb, that's how it works. In a nuclear reactor, it's a far more controlled reaction. They have what's called a fuel rod. And on the fuel rod are small fuel pellets, chunks of this stuff, but smaller. Okay? And they just lower it into the path of a particle gun, which just shoots like alpha particles and neutrons, free neutrons and stuff at these and causes the fission reaction to happen. But we can control how quickly the reaction happens. If we want to generate a lot of electricity, we lower more of the rod into the path, and so the fission reaction speeds up, heats up the water that surrounds it, the water boils, turns the turbine, generates electricity. Okay, it's far more controlled. Okay, if we want to slow the reaction, we pull more of the rod out. Okay, that's basically how it works. Everyone okay with that? Everyone kind of likes to know, how does that work? Okay, the sun obviously works differently. Okay, the sun doesn't use fission. This is splitting an atom, which is fission. The sun uses fusion. Okay, the sun is a big nuclear fire. Okay, and what's going on inside the sun is, instead of making atoms split, we're forcing them together. Okay, so inside the sun, you have hydrogen atoms, lots of them, and the sun is huge, incredibly massive. And the sun is so heavy that its gravity is so strong it can actually force atoms of hydrogen, 3 of them, together to form a single helium atom. Okay, in a nuclear fusion reaction. Okay, that generates even more energy than a fission reaction does. Okay, and it's doing that all the time. Okay, forcing these atoms together. Okay, and there's lots of hydrogen there. It's all being turned into helium slowly. Okay, over the next 4 billion years or so, the sun will change because it'll start to run out of hydrogen. And then it'll start to try and fuse helium, and that won't work, and the sun will swell and it'll get really big. It'll turn into a red giant. It'll swallow up the Earth. We won't be around then. Be okay. It's not tomorrow. Okay, it's not tomorrow. Okay, it's billions of years from now. But yeah, that's what'll happen, and then it just won't be able to carry out the fusion reactions anymore because it's not heavy enough, and it'll just collapse on itself, and it'll turn into a little white dwarf. Okay, our sun's not big enough to go supernova. Okay, it has to be a lot bigger. But it's a fusion reaction that's going on. It's altering. Fission and fusion actually physically, not chemically, but physically alter the atom. They change one atom into another. Okay, or several atoms into one other, okay, if it's fusion, right? That doesn't happen in a chemical reaction. In a chemical reaction, we're looking at point number 4, okay, and that is atoms are separated, joined, or rearranged. Okay, everybody good with that? That's where we're going to leave it for today. Okay, so we're going to finish this up tomorrow. There'll be some questions for you to answer tomorrow. You might have to finish them, okay, over the weekend, right? But that's where we'll head to tomorrow. I think there's only a couple minutes left in class here, so we'll call it there. It's a good place to stop.